Ó ṣe rọrùn sí.
Hello, everyone. We'll be starting in a minute. If you could all please mute your mics, just not to cause interference. All right. Good morning, everybody. My name is Dimeji, and welcome to the Niger Automation Hub Bootcamp. I'm one of the program coordinators along with Joseph. So I'll be doing a quick introduction of the bootcamp. A lot of you have already read different things online, but this is just to set the stage for what we are going to be doing today and for the rest of the bootcamp. Okay. So a lot of people attended the events last year. We had a bunch of guys, with some of which you can see in the picture, along with our convener down here, Adiola Adegbite, came together, and we saw that there were some gaps in the automation industry. Different spaces had their own events and communities. Like you see people in the tech space, you see people in data science, you see people doing all stuff, but we felt that there was really nothing as such for automation. There were some, but we just felt we wanted to create something. And we came together last year. I sniped this picture from our LinkedIn page. We came together last year just to organize something. And it started just from a series of discussions. And then we started reaching out to different stakeholders in the industry. And the event came together. We had, I believe, well over 300 attendees last year. And different speakers, engineer Dakosho Sonya, probably some people consider it to be the #1 automation person in the industry. We had the president of ISC and the director of DEM Controls, engineer Wale Akonde, and is the head of ISC Europe, Middle East, and Africa. We had Miss Velema of Schneider. So a lot of good came out of that event. But as we completed it, we started thinking about ways to actually grow the impact and to create a structured program for people that are trying to come up in the industry. So go to this next time. Why are we doing this? The first reason we are having this boot camp is to bridge the skill gap in the industry. Sorry, pardon my spelling, for young engineers. So a lot of the people that came for that event are mostly young people, students, people that are in their early careers. We had some seasoned professionals as well as attendees, but we saw that it was a lot of young people, and a lot of them were in school, and because PLCs are inherently expensive, access to the software is mostly being gate kept by people, and we just felt that we wanted to provide that level of access.
So dreams do come true.
I think all mics should be muted, please. So we're trying to create access to young engineers, and also to provide opportunities for young engineers to gain practical experience in the industry from people that are actually practicing in the industry. I'll get into that a little bit later. And the last thing is that we're trying to transition from event-based activities to a structured training system with defined outcomes. So everybody that has ever been in our industry knows that 10 years ago, 15 years ago, 20 years ago, the automation industry was dominated by expatriates. There's nothing wrong with people coming in to come and work on your system and your country, but it became a situation where that would now become the expectation to the exclusion of the citizens and indigenes of the country that were trying to get a leg up. So this is more of just an activity for us to, and we saw that the challenge was, it's not that Nigerian companies don't want to hire Nigerian engineers, but the skill required was just so specialized that a lot of Nigerian engineers did not have it. But things are much better now. We have a lot of established automation companies that have been able to train indigenous engineers, and the number is growing. We have new automation companies coming up all the time, and that has actually helped um, to groom more local engineers. I got my start at an indigenous automation companies, people that came together to create this event. So the hope is that if through this structured training, we'll be able to create engineers with the required skills that will allow them function in the industry without any fear of discrimination. So just a little overview of the program outline. We decided to break it down into three broad categories. We have electrical design, which is what we are going to be starting today. And for that, we'll be using EPlan. We have the PLC programming. Can anybody still hear me? I don't know. I feel like I just went. So we have the electrical design, which from April 25 to May 7. And we are starting that this morning. We're going to be doing EPlan. Then we have the PLC programming and HMI design, which is going to be from May 9 to June 11. And then we have the introduction to robotics, which is going to be from June 13 to July 2. So that is subject to some change, and any change will be communicated in due course. So the program outline is mostly going to be the training days are Tuesdays, Thursdays, and Saturdays. So for the first part of the course before robotics, it's going to be every Saturday, 10 a.m. and in the Tuesdays and Thursdays, 8 p.m. And then for the robotics, we have to adjust our schedule a little bit. Is Thursdays, 8:30 and Saturday, 5 p.m. And any schedule changes will be duly communicated through the official channels and on the LinkedIn page as well, or on the Nigeria Automation Bootcamp or Bootcamp WhatsApp. So yeah, what are the metrics for participation? Because one of the questions we've been asking ourselves, sorry, I'm trying to hear somebody. Yeah, one of the metrics for participation is that we are trying to ensure that we get full participation from people who are going to be involved long term. We don't want a situation where people are just popping out and want to enforce some level of consistency and discipline. So minimum attendance is 80%. We're going to be taking random attendance during classes. The minimum attendance 80%, and that's the strict requirement. If you fail to meet 80%, then you are essentially disqualified from any of the things that are going to be shared at the end. And like I said, random attendance will be taken. We're not going to tell you how, but you will know when it's time to take the attendance. So then there will be periodic quizzes, assignments, and capstone projects for each course. You have to submit all of them. That's also a strict requirement. So then at the end of each week, you are meant to create weekly summaries of the content length, and you have to share it on LinkedIn. So that this one way is a way of giving you visibility so that you can document your journey. That's one of if there's any advice I give people, is that always ensure that you document whatever it is you are doing on social media. Then the top performers will be selected based on weighted scores across all courses. We're not going to give you the exact distribution of the weights, but not all the courses carry equal scores. But we are going to aggregate the scores and weight them according to the individual modules. So what to look forward to at the end? So there's going to be a certificate of participation for people who meet the requirements that were previously stated. And then the top 5 participants are going to get paid internship opportunities at partner companies for a period of 1 year. And just to note, the internship opportunities are not an offer of employment. It's at the discretion of the partner companies. After your internship, if they feel that you did not do well enough or they don't want to absorb you, they are under no obligation to do so, and to be clearly stated before you are offered, so that we don't run into a situation where people begin to make complaints. Yeah, we just like to make that very clear at the beginning. Yeah, so I think that's just a quick overview of what to expect, and well, yeah, I wish you all the best. Thank you very much. So, Alfred, I'll be handing over to you for you to start your class.
Okay, good morning, everybody. If you can hear me, let me get like a reaction. So I'm sure my mic is working. Okay, thank you. So the reactions are becoming a bit too much. You should not explain my laptop.
All right. No wahala, no wahala. They can hear you. You can stop reacting now. And people are still
So,
reacting.
okay, so it's a beautiful morning and another weekend. And I'm sure you all had a beautiful and let me not say a stress-free week because we are engineers. So it's almost stressful every week. But I'm sure you are getting the rest you need this week. So once again, I am Aggie Alfred, and I'll be taking this session on industrial panel control design with EPlan as our major topic, EPlan electric PEs. So let me share my screen. Okay. Okay, so if you can see my screen, please, let me get another reaction.
Yeah, we can see your screen, sir.
Okay, okay. So, like I said, once again, welcome to this session. I promise it's going to be a beautiful journey, especially for young engineers. So I'll welcome you to what I genuinely believe is going to be one of the most practical and career-defining training program you will go through as a young engineer, because we are particularly targeting the young engineers. Though I'm sure we have different engineers on board with a whole lot of experience. It is beautiful, but our focus will be on the young engineers. So as to give them like a roadmap, the knowledge they require, that knowledge they feel everybody is holding, it is scarce. It is, I know automation, electrical design, it's actually a lot. And I promise you, what you just need is the roadmap. If you get the roadmap, you know your basics, then you can start the journey. Even, I would say, almost without a teacher. So please, once again, please mute your mic. Mute your mic. Drop your questions in the chat box if you need to. If you have any questions, we'll be attending to them after the whole session. And fasten your seatbelt, because today is going to somehow be a long one. And I'm sure you all have your books, because one thing I love doing is I love writing. No matter how I write in that jota, as far as it's my jota, is my language, I'll write it anyhow, as far as I will understand. So get a jota, get like 4 pens, because we are going to do a lot of writing today. So another thing is, from the group, I know we'll be having challenges with installing the software. I've been seeing a whole lot of questions. So I've decided to upload the software I'm going to use, the software I have on my laptop, on a drive, and also do an installation video. So I was trying to provide links and all of that, but I see that you all still keep getting issues. So I'll upload my own setup on a link, share it to the group, and also try to do an installation video. And today we'll particularly not be doing so much on the software. We just need our background to be strengthened before we go into the software. If you are still with me, let me get a reaction, please. So, like I said, for the next 2 to 3 weeks, all of us here will be going to, we'll definitely be working together to build something real. We are not just doing theory on a whiteboard or teaching you basic theory, but we are going to do an actual professional grade industrial control panel design. Though it might be basic, but it is professional grade. And it's going to be documented from scratch using EPlan, like I said, EPlan electric P8. So before we dive in, I want you to take a moment to set your expectations correctly, because I would say this is very important. I would say by the time you finish the whole of this training, from the electrical design to the PLC to the robotics, particularly the electrical design, I bet you as a young engineer, even if you be getting the basics, I promise you the advanced part will not be so much. You'll be able to sit in front of a customer's specification document. You'll be able to open EPlan Electric P8 and begin designing a complete PLC, not just the PLC control panel, but any control panel with the proper schematics, proper documentation, proper reports that a panel builder can take straight to the workshop floor. So it's just like music. In music, you don't need to like teach me your language. As far as the tonality is correct, the time signature is correct, everything is correct, you are definitely going to, we would sing the music as if we own the language. So if your documentation is right, then the panel builder will build the panel as if you two planned it together. And so, like I said, we will not be touching EPlan just yet. Not deeply. Today will just be about building the foundations in your mind, because the truth is, if you open EPlan without understanding why it exists, what problem it solves, where it fits in the real world of industrial automation, it will just look like a drawing tool. And I promise you, EPlan is not just a drawing tool. It is something far more important than that. And I want you to understand the difference from day one. That's today. EPlan is very big. EPlan is a lot. EPlan Electric P8 is just one out of the several environments in EPlan as a whole. We have EPlan Pro Panel, we have EPlan Fluid, but particularly we are using EPlan Electric P8. If you ask me, I'll say it's the mother of them all. This is where you do the schematics. This is where you do the very important things. And so let's get started into today's presentation. So if you are still with me, I'll be asking for reactions always. So let me get reactions, please. Okay. Okay. Thank you. So we'll be starting by, I'll start by asking a very simple question. If I may ask, what do you understand by the word industrial electrical design? So let me not make the whole session so, how will I put it now, too lengthy. Let me just say, think of it in this way. Think about any machine you've seen up to, okay, let me use a basic example, the pumping machine in your house. I'm sure most people have a pumping machine. You have where you switch on this machine. For those that have been in industries, think of any machine that you have seen in a factory, a conveyor belt, a water pump, a packaging machine, a lift system. That's very popular. Anything at all. So how do you think that these machines know when to start, when to stop, when something has gone wrong, when it needs to shut down immediately, in order to like protect the operator? The answer in every single case I've mentioned is a control panel. So don't have the mindset of you hearing that this is a control panel and you think, is this very big thing on my screen? There are very they are small-sized control panels. They are lighting control panels that are very small. So you don't want to just believe that anywhere you see control panel, you want to believe that it is very big. It is very big. It is something very complex that I cannot understand. I met an engineer in CCN one time that said, for engineering, the cheat to understanding engineering is from the name, you almost get the meaning. So control, you have access, come in, don't come in, stay, do this. And you have a panel that's like assembly of things, people that say, okay, we are giving you this instruction not to do this. So don't always think a control panel is something very big, something very, you can have a small, control panel. You definitely can. And so, like I said, that for every case, the answer is a control panel, and that control panel. Sorry, can you please mute your mic? Okay. So, and like I said, the answer is a control panel, and control panel was designed. I would say control panel are always designed by an electrical engineer, someone who sat down with what the customer wants, the customer requirements, thought through every component needed, every wire, every protection device, every input signal and output signal, and they document all of that before a single piece of metal was cut or a single cable was laid. So you can have a group of people that that come together to like plan. It's particular. Somebody can build a control panel, while you can also have a group of people planning on how to build a control panel. And so if I'm making this concrete for you, I would say a control panel at its most fundamental level is an assembly of electrical components housed inside an enclosure. So if you can see my screen, this is what a control panel looks like. Sorry. This is what a control panel looks. I'm trying to adjust this. Okay, so this is the housing I am talking about. You have your cabinet and you have everything inside. So this is basically what you see, and if you're trying to imagine what, but this is like I said, this is a very big control panel. You have very small ones. And I want you to understand something that many beginners miss. A control panel is not just a box full of wires. It is an engineered system. Every single component inside has a function. They have a rating, they have a position, and a connection to something else. And before that panel is assembled, every one of those components must be documented, drawn, labeled, cross-referenced, which is the part I like part about EPlan, and verified. Documentation is what, so if I say that documentation is what we call electrical design documentation, and producing it professionally is exactly what this course will teach you to do. So you just don't want to go out to build a panel anyhow, and you just feel you can just drag a contactor and just arrange anything. It will be shocking to you that you have a whole lot of panel builders that don't even follow the principle on how to build a proper control panel. Now, if you can still hear me, let me get a reaction, please. So I am not like talking to myself.
Yes, I can hear you.
Okay, thank you.
Yes.
So now, if we talk about the types of control panels, like I said, we have the power control panels, we have the motor control centers, we have the programmable logic control panel, that's the PLC panel, we have the lighting control panel. And if I'm to talk about the first one, which is the power control panel, this is a big one. This is a PCC panel is typically the main incoming power distribution point for an entire facility or a section of a plant. What this panel does is it receives high voltage or medium voltage supply from the utility or from the transformer, and then distributes it to smaller panels, distributes it to panels like the motor control center and other loads. So you're thinking of it as the master distribution hub. in a large manufacturing plant or let me say an industrial facility, you typically find one or more PCC panels feeding everything else downstream. I'll tell you that these panels are large. They are complex and handle significant power levels. So you just don't want to go through these panels. There are a lot of safety, a lot of instructions to people that are even meant to handle this panel. And if I'm to talk about the second type of panel, which is the motor control center panel. I'll say this is probably the most common panel type you will design as an entry-level electrical engineer in the automation space. So an MCC panel is dedicated to starting, stopping, protecting, and controlling electrical motors. It contains what would I call it now? Starters, contactors, overload relays, circuit breakers, and the associated control wiring for multiple motor circuits, and all in one centralized cabinet, like I said before. So every production line, pump station, or conveyor system that drives motor will have an MCC panel associated with it. So I'm sure you all in your schools have done, say, at least even if it's theoretical, star delta, direct online, this and this. You definitely know how these things work. You have to design it. It's not just drawing the whole. I'm sure. Let me not say 50%, because I know how the Nigeria education system works. You know how to draw that diagram, but you cannot even visualize how these things work. So the MCC control panel is controls motors, start, stop, a whole lot of things. And if you're talking about the PLC panel, this is where I would say this is where automation truly lives. And automation should not be new to you, because I'm sure most of you have handled Arduinos, ESP32, and all of that. So having a PLC is like having the bigger size, the industrial size of what those controllers can do. And like I said, that this is where automation truly lives. And this is the panel type we'll be focusing on most heavily during this training. So even if we might not design, kindly mute your mic, please. So even if we might not design a very complex PLC control panel, even if it's an MCC panel, since it's a beginner level bootcamp, we'll still show you how PLCs are imported into EPlan, how they are connected, and all of that, and you get to see it. If there is time, we will do a basic 3D construction of these panels. So you get to see how everything is so beautiful that if you give the proper documentation to a panel builder, even if you might be the electrical designer and still build the panel builder. So you are giving back yourself the proper documentation, and you'll be happy that I did my documentation well, and at the same time, I'm not stressing that I am building a control panel. And so for the fourth one, which is the lighting control panel. So as the name suggests, the panel manages lighting circuits in buildings. I'll even say we all have this small control box in our houses with circuit breakers that we use to control lighting, to sockets. That is a mini control panel. That can be compared to what I call like a lighting control panel. So they are in buildings and factories, warehouses, outdoor areas. And while it may seem simpler than others, lighting control panels require very professional electric design too. Proper circuit protection, correct cable sizing, control relays, and sometimes programmable dimming, or should I say switching controllers. So I'm sure for all of you that are young here, the young engineers, I'm sure by now you can picture the type of panel you think you will encounter when you start working in the industry. I am sure you want to like say, what type of panel will I see? Will I see an MCC? Will I see a power control panel? Will I see a lighting control panel? So for the next session, I am sure you understand what this is. Still talking about control panel, but now we want to talk about why does documentation exist before the panel is built? For our first point, I've said why every industrial machine requires a control panel to operate. You basically have the understanding. And for the panel houses, you see your panel with a power protection, PLCs, relay, contactors, you see terminal, you see a whole lot of things. We'll still come back to that. But a particular point I want to make clear in this section is why documentation exists even before the panel is built. So I would say the reality of industrial panel building is when the panel builder goes to the workshop to assemble a control panel, they cannot just guess. They cannot improvise. They cannot ask the engineer, where should I put the contactor? Or which wire goes to the terminal? Because the engineer might be a 1,000 kilometers away working on the next project. The panel builder needs to build a complete should I say a complete set of documents that tells them everything: what component to order, where to mount them, how to connect them, what each wire is called, and where each wire starts and ends. And I'll tell you that as a beginner electrical designer, you must build your background well, up to knowing your as small as your electrical symbols. You want to know them very well. So don't be scared that you have to cram every symbol. The word is getting better that if I import a contactor into EPlan, it automatically gives me the symbol. I'm not like drawing manually, maybe in AutoCAD or something. Even I'm sure sometimes there are DWG files of these documents. But so you don't really have to like cram the whole control panel symbols and want to kill yourself. But you should know most of them because you will tend to like read electrical drawings. And you even tend to like see electrical drawings that are incomplete. If you see the complete ones, you see a legend page, you see what they explain. If you don't see legend page, you see a table of content that tells you, okay, these symbols that you can cross-reference, and you say this symbol is, okay, this is a switch, this is a, so please mute your mic. Yeah, thank you.
Sorry,
So you don't
quick
really,
observation.
okay.
I'm thinking maybe everybody can be muted, like from the host end. Everybody can be muted.
Can the host please help me with this? Okay, thank you. I'm sure it will be handled. So you should be conversant with those symbols. And let's say after this session, I'll send the document containing some I'll send a document containing some symbols so everybody can like familiarize themselves with those symbols. And so the complete set of documents is what, like I was saying, is what that electrical design engineer produces. And when those documents are done correctly, a panel builder who has never seen that project before can pick them up, go to the workshop, and build the panel completely for the first time. So, and when those documents are done incorrectly or not at all, you get wiring mistakes, you get reworks, you get commissioning delays, and in the worst case, safety incidents. I bet you have seen projects where poor electrical documentation caused days of delays on the factory startup, costing clients, I'll tell you, tens of thousands of dollars in production losses. I've seen a panel where I've been there and they told me there's no documentation. I've been using it like this. We don't know. So if you don't build your background knowledge well, you almost cannot even troubleshoot this panel. I'll not even blame an engineer that says, okay, if you don't have a documentation, I'm not working on it. It's supposed to be the standard. So then they have to go back to physically looking at that panel and start doing the documentation for everything. So this does not make sense. And this is what bad documentation looks like in real world. So if I'm to give you okay, so let me say if you imagine a conveyor belt in a bottling factory, this conveyor belt is part of a production line. That bottle, water or beverage, it needs to move bottles from one station to another, detect bottles that are present, start and stop control, and respond to fault safely. So, and inside this, you definitely will want to see different type of components inside that control panel or attached to the control panel. You see a motor, you see a PLC. If you don't see a PLC, you see contactors and relays, you see sensors, you see that housing that will house everything and make it complete. And this is what electrical design, this is what electrical control panel design looks like. And I bet you that is why you are here. So if, okay, yes. And before we go into the next section, if you can still hear me, let somebody just unmute and say they can hear me.
Loud and clear.
Yes, I can.
Okay, thank you. So for this part,
We can hear
this
you.
is one part. Okay, I can hear you too, thank you. So this is one part everybody is not supposed to joke with. I have seen a whole lot of control panel builders not even following any standard. As well as there's contactor, as well as there's relay, they put it inside an enclosure, they'll bring it to you, and you will do it. So if you have your books, if you have your biros, this part might seem a little long, but it is worth it. So you want to make sure that you are listening attentively in this part. So, and in this slide, you see a collection of logos on the left. UL, CSA, NFPAC, NEMA, NEC, all of them. These are the marks and bodies that defines, they define how industrial control panels must be designed. So let me give you how they must be designed, they must be built and verified around the world. So why do you think sometimes you buy Pepsi bottle and for all of you that used to sell Zobo low-key, you buy Pepsi bottle and you can still use the cover to cover Fanta bottle. Do you think they just go to the factory and say, let me copy what your bottle looks like and let's use it? There is a standard, and that's where it comes in. If you are creating a PET bottle or something for soda, you must follow the standard. Your cup must be, the cover must be 2 inches, this is by diameter, this. Everybody gets the standard, everybody manufactures their bottles, and then you can see that, oh, I'm using this bottle for this. It is not, there have been a lot of work, people have sat down to like arrange the standards to make sure that, yes, we safety-wise, we don't want engineers to be jumping from one place to another. Different markets, different industries, and different clients, we reference different combination of these marks. And as a professional electrical design engineer, you need to know what each one means and what it demands of your design. So I would say for a basic electrical panel builder, we are going to focus on 4 standards listed on this slide, because these are the 4 standards that will appear mostly frequently in your professional practice. And these are the 4 that will directly influence your decision, the decision you will make if you are using EPlan. And so let me walk you through each one carefully. So like I said, make sure you have your books, because you can read about these standards, but I bet you if you download these standards, have anyone seen a law document before? You are going to see it's like you're saying, I'm not saying you see subsection 1, but you will see for the panel must meet this requirement, you will see a whole lot, and you definitely want to read a whole lot from this. And so that's why I'm saying, if you can concentrate in this session, you will get a lot. You will definitely get a lot from this. So now let us start from the IEC 61439 standard. So I describe it as the international benchmark for low voltage switches and control gear assemblies. So IEC 61439 is published by, IEC means International Electrotechnical Commission, the same international body whose symbol and drawing convention we are using throughout the entire training program. So I'll say this standard is the primary international reference for design, construction, and verification of low voltage switchgear and control gear assemblies, and which is the technical description of what an industrial control panel is. We mentioned that there are PCC panels, and so if you want to build low voltage panels, you definitely want to keep this standard handy. It's a beautiful world now where you don't have to read the whole standard. You can download the standard, you can give it to AI, it gives you the key points you want. But then, if there are times you have a team, they can go through the standard. And so, if I'm to unpack the face of the IEC 61439 standard, low voltage switchgear and control panel assemblies, this is important because you understand exactly what it means. Low voltage in IC technology means system operating at voltages up to 1000 VAC. So if you have done panel, if you did panel, sorry, I'm saying panel. If you did power, you should understand how voltage are classified. Low voltage stops at 1000 volts VAC, and this is because of the what will I call it now? The arc quenching medium and the insulation method. So low voltage for systems operating at voltage up to 1000 VAC or 1500 DC voltage. So virtually every industrial control panel you will design in your career operate within this range. 400 volts. I'm not saying you might not get to a point where you have to the truth is, when you start seeing medium voltage and high voltages, they cannot fit into a control panel again. So you cannot put an SF6 circuit breaker inside the control panel. So what you'll be dealing with mostly is the as regard control panel is the low voltages. So like I said, that virtually every industrial control panel you will design will be within this range. 400 volt AC 3-phase, 230 volt single phase, 24 volt DC control circuit, all falls under IEC 61439 standard. So IEC 61439 does not just govern individual components, it governs the complete assembly panel as a system. So even if every individual component in your panel, every NCB, contactor, terminal is independently certified to its own product standard, the panel as a whole must still comply with IEC 61439 as an assembly. And so what does IEC 61439 actually require of your design? So let me give you the key areas. 1, it specifies temperature rise limit. The maximum, I would say the maximum permissible temperature rise of components and conductors inside the panel under normal operating system. This is important because I would say it drives decision about panel ventilation, the rating of components in enclosed spaces, and I would say the selection of appropriate cable cross sections. And so another point is it specifies short circuit withstand strength. So this is important because I would say your panel must be able to withstand the short circuit current available, and it's at its supply point without you having a catastrophic failure. So this drives the selection of correctly rated circuit breakers and bus bars. And so the third point I will mention is it specifies clearance and creepage distances. So you don't want to build a control panel where you will just squeeze. Sorry, who is trying to write on my screen? Okay, so it's like I said, it specifies the short circuits. Okay, so it specifies the clearance and the creepage distances. And so This talk about the minimum physical distances between live conductors and earthed metal work to like prevent flashover and tracking. These distances are very important and they depend on the voltage level and also the pollution degree of your environment. So you see why your IEC standard must be very important. Your IEC standard is very important, 61439. Another point is it specifies protective earthing requirements. How all the conductive part of the panel that are not intended to be live must be bonded together to protective earth. This panel will tell you how you have to make sure that your earthing. Is somebody saying something? So it tells you how your earthing system must be up to standard. And so we have 2 more points before we go to the next standard.
Excuse me.
Okay.
Yeah, some of us are trying to write. I feel you're somehow a bit faster.
Oh, okay.
Thank you.
No problem. Okay. So, okay, I'm also trying to check the time because the session is supposed to end by 1 o'clock. But it's all good. I'll reduce the speed. So another point is I talked about the protective edge requirements. How all your components must be bounded together to protective edge. Making sure that nobody gets electrocuted when they go to the panel. Fault current does not affect the panel. Another thing is documentation requirements. IEC 61439. What information must be provided with the completed panel assembly, including the design documentation, the verification records, and the marking requirements. And so I would say, as an electrical design engineer, IEC 61439 is your primary compliance reference for every panel you design, no matter how little. And so when the client specification says, or you see somebody, and I'll tell you it is very common. You say the panel shall be designed and manufactured in accordance with IEC 61439. They're telling you that this is the standard they are invoking. And I'll tell you that you should know it. And like I said, you cannot cram it, but keep it handy, reference it, and design to it. The whole idea about the standards is making me remember when I did engineering law in school. I like when they will say, okay, according to subsection this, an engineer will have to pay so amount. You are liable to. I was always attentive during engineering law classes. So if you have if you have your standards, I would say, look, it's like you are going through law documents, and you want to make sure you are attentive throughout every session. So if you are still with me, let me get some people just unmute and say they can hear me.
Yes, I can.
Carry on, sir. We're together.
Loud and clear.
Okay.
I can hear you,
Okay.
sir.
Thank
Loud and
you. I
clear.
can hear you.
Captain.
So if you have to talk about the second standard, which I named the construction gold standard, UL 508A, personally described as the construction gold standard, and the most recognized how-to manual. That is, how do I want to do this for building an industrial control panel? So UL 508A is published by Underwater's Laboratory, and they are an American safety certification organization that is one of the most recognized and respected testing and certification bodies in the world. The UL mark that you see on the logo panel, that is this you are seeing on my slide. It is with the circle. It is one of the most widely recognized safety marks globally. And so this standard is specifically titled Standard for Industrial Control Panels, and it is extraordinarily detailed and prescriptive. So where IEC 61439 sets performance based requirements, telling you what the panel must achieve and all of that, UL 508A is largely prescriptive, telling you exactly how to build that panel. I think I have a document on a summary of how you're supposed to, a summary of UL 508A standard, and I'll share it. And so this is why it ends the description of the most recognized how-to manual. It does not just say protect against overcurrent. Sorry, mute your mic, please. It tells you exactly how to size the protection, exactly where the wire colors, exactly what color wire colors to use, exactly how to label terminals, exactly how far apart components must be spaced, and dozens of other specific construction requirements. Let me give you some concrete example of what UL 508 specifies. So one, take this down. It is the wire color coding. So UL 508A, like I said, specifies in North American panels, green or green with yellow stripe conductors are reserved exclusively for protective earth connections. Black conductors are used for, sorry, whoever is writing on my screen should please stop. I don't know if the host can do something to this. Okay, so like I said, UL 508A. I was talking about the wire.
Yes, we were talking about the black. Is that for
Yeah,
the
the person writing on my screen is distracting me. Okay, so I was talking about the black conductors used for undergrounded power circuit conductors. White or gray conductors are used for grounded neutral conductors. No other colors may be. No other colors may be. Please mute your mic, please. You are distracting me.
Only penthouse.
Guy.
Sorry,
Sorry, I didn't
please.
know.
The host can restrict all this distraction from his end.
Yeah,
Please.
I'm asking I'm a co-host, so I'm trying to Can you hear me, please? If you can hear me, let somebody speak up. Okay, so like I was saying, I was talking about the color code, the wire color coding before I got distracted. So white or gray conductors are used for grounded neutral conductors. So I'm still talking about the North American panels. So we all have different color codes for different countries. You might even have a different color code that's related to your in-house standard. But you can get basics of this color code from this standard we are discussing. And so another point is wire marking. Every wire in UL 508A compliant panel must be marked at both ends with a consistent identification system. So unmarked wires are not just acceptable in this standard. This requirement alone has significant, I would say it has significant implication for how you document wire numbers in your EPlan schematics, because the wire numbers in your EPlan drawing must match the physical wire markers in the panel build. So for the third point, we have the component spacing. So this standard, it specifies the minimum spacing between components on a DIN rail and in the panel enclosure. So this is important because it will allow for heat dissipation, maintenance access, and prevention of interference between adjacent devices. And so for the next point, we have overcurrent protections. It gives extremely specific tables for sizing, what will I call it now? Branch circuit protection for different types of load, from motors to transformers to lighting circuits and so on. And I'll tell you that the tables in this standard are more prescriptive than that in IEC 61439. And I tell you, they leave room for engineering judgment, if you ask me. So let me get reactions if you are still listening to me. And thank you for clearing my screen. So here is the question. Let me give you a practical question. You probably will be asking, if we are working to IEC standards in Nigeria, and for international clients, why do I need UL 508A? 3 reasons. First, for some Nigerian projects, but I would say particularly in the oil and gas sector, where American companies or American project management consultants are involved, they will specify UL 508A compliance or request UL listed panels. If you encounter this requirement and you do not know what UL 508A entails, you cannot even design to it or even communicate intelligently about it with the client. The second reason that most of the requirements in UL 508A, they represent genuinely excellent engineering practice. Requirement that makes your panel safer, more maintainable, more reliable, regardless of which geographic market they are destined for. If you understand UL 508A, I would say it enriches your engineering judgment, even when you are working with IEC 61439. And lastly, I would say the global automation industry is increasing. Is increasing. So a Nigerian engineer working for a multinational company may design panel destined for multiple markets simultaneously. So if you are having awareness of both IEC 61439 and UL 508A, I bet you it's a requirement. It's a good one, and I would say it's a professional asset. So we have talked about 2 standards now. Now let us talk about the NFPA 79, the machinery safety standards. And this dictates how emergency stops and safety interlocks, basically dictates how emergency stops and safety interlocks must behave. So this standard tells you that for this your panel, what are the safety in place? You not just say, okay, let me just put an emergency stop and just cancel the whole process and just do this. There are standards that tell you that if you must have interlocks, if you must have emergency stops, this is how you should do it. And so NFPA 79 is published by the National Fire Protection Association. So I'm sure you can even see fire on their logo. You can see fire on their logo. So it is titled Electrical Standard for Industrial Machinery, and it governs that electrical equipment associated with industrial machines, that is the wiring, the control circuit, the safety systems, and the operator interface. So I would say where UL 508A governs the panel enclosure and the internal construction, this standard, that is the NFPA 79, governs how the electrical system of an industrial machine must behave, particularly in terms of safety. So I will add this to it that its most significant provisions relate to emergency stop systems and safety interlock, which is why I described it as the machinery safety standard. So again, write 4 points under the standard. I already told you standards are important, and that's why this session is taking quite a lot of time. And so I'll be giving 4 points under the standard. First is the emergency stop requirement. NFPA 79 specifies that emergency stop devices must be red actuators on a yellow background, making them immediately identifiable by operators. That is, even under stress or in poor lighting. It specifies that emergency stop circuit must use normally close contact. So I'm not saying you will not see emergency stop buttons with normally open contact, but a standard emergency stop button should have a normally closed contact. The ones with normally open are those emergency buttons that when you hit them and they close, they are like sending maybe signals to your PLCs or your control panels. So a basic emergency switch or emergency stop button must be normally closed. And so when you hit that emergency button, the panel opens. So like I said, yes, it is achieved by opening the circuit. So I would add to it that it specifies that emergency stop circuit must be monitored, meaning the control system must detect if the emergency stop circuit develops a fault, not just if the button is pressed. So and it specifies that emergency stop button functions must be self-latching. So I'm saying this means once you activate it, the emergency stop must remain active until it is deliberately reset by an authorized person, preventing automatic restart after an emergency condition clears. So all these conditions are under the one of the conditions under the NFPA 79. I've talked about how the emergency stop button must work. So you cannot say because you have an emergency stop button, even before you put the normally open contact in an emergency button, the basic thing that must be there must be the normally closed contact. So what you want to do is you want to break that circuit if there is a problem. You don't want to connect the circuit if there is a problem. So your basic emergency stop must be normally closed. If you have the normally open, then it's another advantage. So I would say for legacy panels, let's say if I hit an emergency button, the O panel goes off. But since we don't have PLC has been in existence for long, but let's say for panels that don't have PLC, and you want to use your red bulb as indication. That's where you have a normally open contact on your emergency button, or you pass it through a relay and do the whole normally close and normally open function. So what you are doing is immediately you hit that emergency stop button, ignore the light and everything. First, the panel will go off. Then the normally open contact on that emergency button closes and indicates. That's where you not see your red light, that there is a fault. And if you are now coming to advanced system, that's where you see that, oh, your HMI will show emergency active, acknowledge, or clear before you do this and do that. And so the next point I'm talking about is the safety interlock requirement. So I would say a basic definition of safety interlock is a simple ATS system, so automatic transfer switch. And this is what I mean. You have a generator, you have a NEPA. You have NEPA connection to yours, you have generator connected to yours. But you want a system whereby when NEPA comes, generator should go off. When generator is on, NEPA should not be on, something like that. You have to interlock the two. So it's like saying, I'm looking for a simpler way to put it. you have two people that they are supposed to enter a room, but I don't know if this example will serve, but my child is restricting the other person from entering that room, while the other person's child is restricting me from entering my room. So one at a time. If this is on, this should not be on. You don't want to have a case where generator and NEPA supply both enter into your building at the same time. And the NFPA 79 talks about how interlocks should behave. And this is the details. It specifies that guard switches, door interlocks, and other safety devices must be integrated into the control circuits. Safety interlocks must be designed so that opening a guard or accessing a danger zone removes power from the hazardous motion. Exactly what I explained before. So you are not just having signals to control signals. You are not just the signals that the control system has to stop. It must be that, oh, if you are entering into an unsafe place, then let that whatever safety device you have put in there stop. So you have used that safety device as an interlock to the whole process. You understand? So, and I would say the distinction is important because a software only interlocks. Where will I put it? How will I put it now? The opening, if you say the opening, if you're opening the guards, it sends a signal to the PLC, which then directly breaks the commands to the motor. So if I use my emergency button as an interlock, instead of me connecting a start button directly to my motor, and while the start button cable now is going directly to my motor, I then put in between the normally close of an emergency button or the normally close of another system. Let's say a safety system. I've done like a mini interlock. So you are saying for this current to flow through the motor, there must be a safe condition. So if there's no safe condition and anybody tries to pass, it opens, not allowing that current flow to the motor and not allowing whatever system you have work. This is another very important safety condition. And so for another important point, which is the last point I'll be giving you as regards NFPA 79, is supply disconnection. That's your main supply disconnection. How it's meant to be built. So the NFPA 79 specifies requirements for the main supply disconnecting. Main supply disconnecting means that how do I disconnect my main supply? Will I have to like run to the panel and just open the panel and start to drag one very big isolator? And so what this point or what this standard states about this point is that it must be lockable in the open position. It must be readily accessible because that is like the main point. If you have been to transmission company, you see that even if they off their breakers, they still make sure there is isolators that you make sure that you are physically seeing that I have disconnected this thing. It is accessible. And so if you do all this, you are disconnecting all grounded supply conductors simultaneously. And now that we have talked about this standard, I've mentioned 3 points, which is the emergency stop requirement, the safety interlock requirement, the supply disconnection. And so NFPA 79 is I would say it's an American standard, but its safety philosophy, fail-safe design, hardware interlocks, monitor safety circuits, is universally, is, how will I say it now, accepted worldwide. It is valid worldwide because even with your common sense, if you see that somebody arranged this standard and you go through the standard and you say that, oh, this makes sense, then tell me why you should not accept it. And I would say it is reflected in the equivalent European standard. There's another standard which is IEC 62061. And so you will see that this NFPA 79, engineers have taken their time to declare the standard to say, yes, if you do this, you will have a safe control panel, a panel that can be operated safely. So without taking much of your time, let's do the last standard out of the this is just the 4 basic standards you're supposed to know as a beginner. Like I said, you don't have to cram everything and start thinking of this standard, but it has to be in handy. You can have a list, generate key points, go through it, know that you are meeting each standard before you are building that control panel, no matter how little it is. And so for the last standard, which is the IEC 60529, this is the Ingress protection rating. That is IP. IP rating, I'm sure you have seen IP rating everywhere. IP rating means Ingress protection. And so IEC 60529 is the standard that defines the IP rating system. And I would say, I would be surprised, like I said, that if there's anyone in this room who has not encountered the term IP rating before, you almost have seen it everywhere. It appears on virtually every electrical enclosure, every industrial sensor, every outdoor electrical fitting, but understanding exactly what these numbers mean and how to correctly specify them for different environments is essential. It is very, very important. And for IP rating, it always have 2 numbers attached to it. Take this, very important. If you check online, you definitely see it. But it is I will summarize what those numbers means. IP rating has 2 digits attached to it in a standardized way. And this tells how well an enclosure or a device is protected against the entry of solid objects and liquid objects. So if we are to decode those 2 digits precisely, I'll tell you what they mean. And now I'll go a bit slower here, and I want you to note it. So let's say you see something like, you see examples like IP65, IP56. So I want to tell you what the first digit means and what the second digit means. So you would see 0, for the first digit, we have 0, 1, 2, 3, 4, 5, 6. The second digit too, we can have 0, 1, 2, 3, 4, 5, 6. So there are different combinations, 0, 0, 5, 6, 6, 5, like that. So those numbers will tell you what kind of protection that that control panel gets. So if you are still with me, let me get reactions to be sure that, okay, thank you, Emmanuel. So now let us go through the 4 important digits of what the IP rating tells us about. Now, the first digit, that is, let me give you the example again, IPXX, 56, 65. So the first X, the first digit, under that first digit, 0. So I would say the first digit means protection against solid objects. So that's basically what the first digit tells you. Then the second digit tells you, so you can do a table in your notes or something. First digit, protection against solid objects. Second digit, protection against liquids. And so for that first digit, X1, so let's use the mathematics way, X1, X2, IP, X1, X2. So under the first digit, 0 means no protection. That is, you are saying the enclosure offers no resistance to entry of solid objects. 1 means protection against solid objects larger than 50 mm. A large surface like the back of a hand, 50 mm, like back of your palm, cannot enter. 2 means protection against solid objects larger than 12.5 mm. So if I'm giving an example, that's like saying your fingers cannot even enter inside that place. Take it. I'm trying to go slow so you can jot it down. 3 means protection against objects larger than 2.5 mm. So if you are looking at this, you are saying tools, let's say thick wires cannot enter. Now, 4 means protection against objects larger than 1 mm. And 5 means dust protected. So this is the one you see almost everywhere. IP5 something. Dust protected. Dust cannot enter in quantities. So you don't want dust to enter. It's telling you that if you see anything IP5, that 5 already is already telling you that dust cannot enter and interfere with operation. Like, it's not like saying 100% dust will not enter. Slight dust might enter, but the quantity that will enter and make your breaker start malfunctioning, it will not allow it. And so 6 means dust tight. 6 means dust tight. So this one, if you see it, you see it as almost, you see it almost everywhere. So if you are seeing what will I call it? If you are seeing systems with IP60, you already know that this is one very big, or how will I put it now? This has a very big protection. They don't want dust at all. So they are telling you that complete protection against dust ingress. No dust enters under any condition. So if you have seen IP6, you are already knowing that. First, this system dust is not allowed. And now let us talk about the second digit, which is X2. That is protection against liquid. Again, 0 under X2 means no protection. 1 means protection against vertically dripping water. Again, 1 means protection against vertically dripping water. 2 means protection against dripping water when the enclosure is lifted up to 15 degrees from vertical. I'll take that again. 1 means protection against vertically dripping water. I want you to note it. Then 2 means protection against dripping water when the enclosure is tilted up to 15 degrees from vertical. 3 means protection against water sprayed at up to 60 degrees from vertical. Water sprayed at up to 60 degrees from vertical. 4 means protection against water splashing from any direction. So you see that there are levels to the protection. 4, if you see IP64, it means 1, this system, dust cannot enter for any reason. And 4 means if you are splashing water from any direction, it will still not affect whatever is inside this enclosure. We are on 4. Now 5 means protection against water jets from any direction. So let's say something like a low pressure hose directed at the enclosure from any angle. So let me say for this IEC 60529, we'll basically be targeting the enclosure. So you are saying if I've assembled everything inside, what's IP protection? Not just the enclosure, but I'm just saying basically, because all your components will have IP protection. So if dust should enter inside your panel, can dust enter inside your contactor? That's another question, because your question has IP protection too. So I stopped at 4. That means 5 means protection against water jet from any direction. That is a low example. I give example of a low pressured hose directed at the enclosure from any angle. 6 means protection against powerful water jets. So even if you have very high pressure water coming from any direction, it will not enter inside that panel. And 7 means protection against temporary immersion. So if you are seeing iPhone users, Android users, say, I want to buy iPhone because it's water resistance. If I put my phone inside water, it will not enter. You do it with care because I'm not sure if you're going to put your iPhone, your $1 million iPhone inside water, it will spoil you. So, but it's just telling you that for them they are telling you that if you put for number 7 now, progression against temporary immersion, it's telling you that if you immerse that subject into water, it will survive for a particular type of for a particular time. But you see, most people still talking about their iPhone, they will put their phone underwater trying to show off, and before you know, your phone will spoil. So it's just telling you that if you dip your enclosure or you dip these devices into water for a particular time of time, it can survive. And 8 means protection against continuous immersion. So the enclosure can be permanently submerged at depth specified by the manufacturer. I'm sure you understand this too. So this is where my first assignment will come in. I would want you to list, okay, let's say, do any combination of the IP rating or list devices. Okay, let me do it this way. You list like 5 devices and the IP ratings after this class. It's not a serious, so I just want you to have it in your notes. You list different devices and the IP ratings, or go online, try to get devices, try to check the IP ratings, come back to your table and see that, oh, when they say this thing is IP this, so it's like saying when you see an enclosure is rated IP54, which is one of, like I said, one of the most common rating for industrial control panels in clean, dry indoor environments. You immediately know that it is dust protected, that is from the X1, and it's protected against water splashing from any direction. If you say IP65, you know that it means dust tight, protection against water jets, and I would say this type of panel are appropriate for like food processing areas or outdoor location. And so if you're now seeing devices like IP67, then it means you are protecting against temporary immersion. And so why does this matter for your electrical design work in EPlan? Because I would say the IP rating of your enclosure is a design decision that you must make based on the environment where the panel will be installed. So there is also standards for what type of environment do you want to install your control panel. So if you are going to that point, we are beginning to go very advanced. If I get hold of those standards, I'll send it to you on the group. It can just be a side read. But as a basic electrical panel designer, you can basically just ask, where are they putting this panel? Is it outside? Is it indoor? If it's indoor, is it a place that they will have access to water and all of that? Then you should be able to determine what IP rating you're using for your control panel. So if you specify the wrong IP or fail to specify one at all, the consequences can be serious. If you have a panel, let's say a small lighting panel of IP20 enclosure installed in food processing, let's say food processing washdown areas, you're exposing that panel to a whole lot of water. Water can enter that panel and now poses safety risk. Components will short circuit, the panel will fail, you will run a scatter, and nobody will help you. And so if the panel fails, production stops, safety incident happens, everywhere will be disrupted. I'm not sure you want to see, for those of you that want to work in manufacturing industries, you don't want to see when a process is disrupted. You will sweat. You see, that point where you have a safety rule not to run in the factory, but you have to walk briskly to the end of a machine that is about 10 meters long just because you have disrupted the process. You will walk like a robot. You will sweat. So you want to make sure for everything you are doing, you are following standards. They do not just wake up to put the standards in place. They've taken time to arrange the standards to tell you that, yes, follow the standards, do this, do that, and you have a very safe working environment. So I've said it before that you should get assignments. Your assignment is check for equipment and their standards. You should be able to interpret that if I'm saying IP54, if I'm saying IP65. So you mostly commonly see 50 something, 60 something, 50 something, 60 something. You will see it almost everywhere. That does not mean they are not others. And so I'll finish this session by saying standard exists because engineers make mistakes. If we decide to allow everybody just work with what they have, there will be mistakes. There will be real-time mistakes. So every requirement, either in IEC 61439, UL 508A, NFPA 79, or even our IEC 60529, it was written in response to a real failure. So if I say that I'm low-key telling you that, let me digress a little bit. Engineers have taken their time to document failures. They're saying that I built a small system. It failed at this point. Why? Because there was no emergency button. Let us create emergency. Let us create something in emergency button. Let us put it in the standard. For anybody manufacturing a control panel, you must have emergency button. Another beauty why documentation is important. So if you're in places where, or in working environments where they tell you, if you fail, we document it. It's not because they want to shade you later and tell you that you failed yesterday, come and sit. 4th of April, you failed by 6 o'clock. No. We want to be able to see vulnerabilities, how to cure these things. If you're into cybersecurity too, you see that you build a system and you attack your system by yourself, so as to see those loopholes. So people have taken time to document failures and see how they would tackle these failures. And so standards are always updated with time. ISA just released a new standard for how HMI should be designed. They've seen it, they've said, oh, I think let's start designing this way. There are some new improvements that will make our design better. So nobody's just waking up any morning and just saying, let me put this here, let me do this, let me do that. And I'll tell you that when you design to these standards, you are not just ticking compliance buttons. You are standing on, I would say, the shoulders of generation of engineers who learned, sometimes at great cost. That is, some might have even died in the process just to see what will happen, what safe and reliable design looks like. So make sure you treat these standards with respect. Design them with all your strength. And when a client or a manager suggests cutting corners on standard compliance, understand the engineering and the human consequence of what they are proposing. So this is the professional standard as beginner electrical engineers we should design to every schema, every project, and every damn time. So if you are still with me, let me get your reaction, please. So I am sure this particular slide was very long. I had to make it long because it is very important. I have seen a whole lot of panels without standard. So you don't want to make sure you follow standards. It is important. It is for your own safety. I've been to somewhere where we went to handle a project and they told me the engineer that was handling the project died 2 days ago. And nobody will wait for you to say, okay, let's see if he gets to heaven and God will, let's mourn him for 2 years. It will continue, the project will continue. So it's always safety first. If you follow this standard, you have a nice panel you have a safe panel. So as beginner engineers, beginner designers, beginner control panel builders, you should know the standards. So don't think because you will not be designing control panel, you don't need to know the standard. What if you get one thing I'm sure you always see is electrical drawings. What if you get electrical drawings and you're like, you don't even know if they follow standards in the electrical drawings. You just go and connect what you're not supposed to connect. Then before you test the panel, you'll be shouting moment of truth. God help me. And you'll be doing sign of the cross, then you press start. You will blow. So you just want to make sure that if you follow the standards, you're rest assured that you're safe. So we'll be talking about the next slide now. I'm talking about control panels. Now we'll be talking about some of what goes inside a control panel. I'm sure most of you have seen this. I've said it before. You have your control panels, you have different things inside. So I used a PLC control panel because the whole bootcamp is driving towards we having a seamless continuation between electrical panel design and PLC and robotics. So that does not mean all your control panels have PLCs in them. PLC is just an advanced part. A basic direct online control panel will just have contactors, terminals, selector switches. We'll not even have the power supply unit, that's the PSU. Somewhere I did it, if you write on my screen again. So it is, how will I put it now? This page tells you the basic things that will go into your control panel. And I want to make you, if you're talking about a PLC control panel now, I want to make you think of it like an hierarchy. There is an incoming power word at the top and the control and signal word further down. So let's work, I will explain that later, how you're supposed to group your drawings, your power first, your control, and all of that. But now let's walk through all these devices. I'm sure we'll know PLC. Even if you don't know, you might have seen the picture or heard of it, a programmable logic controller. So I'll say for a PLC control panel, this is the brain of the automated system. I related it to Arduino ESP32. And the beauty with Arduino now is you can even write some PLC program on Arduino. Write ladder logic on Arduino now. So you don't have to write those plenty code as a beginner. But our PLC now is like an industrial computer. So they continuously read inputs, the read signals come from sensors, buttons, switches. So, and like I said, based on written programs, if you don't have a PLC now, let's say you have a push button and a contactor. And in relay-based systems, relay-based system means systems without a PLC, systems that work only with relays, electromagnetic, all these devices that work with electromagnetic induction, mechanical movement. If you have all those type of panels, you want to control a contactor with a push button. You are basically restricted to pressing that push button and that contactor comes on, releasing the push button and the contactor goes off, basically. And so when you have a PLC, you can do more. If you connect your input device, which is the push button, to the PLC, you connect your contactor to the PLC, you can do a whole lot of things. You can give different conditions. You can say, okay, this thing must not come on after 5 minutes. You can say, okay, if I press this push button 1, 2, 3, 4, 5, that is 5 times, that is when this contactor should come. So you have a brain, an advanced brain. It is not just very mechanical like the relay-based system. And so we have different type of PLCs, and they mostly work on, that doesn't mean you won't see PLCs that work with AC signals. They work with 24 volts DC signals. And like in our bootcamp, you'll be working with Siemens family and the Brandley family. So you should, like I said, you enjoy the session, you enjoy the bootcamp, and you should pay good attention to whatever you'll be learning in the whole of the bootcamp. And so another device is the PSU, the power supply unit. So the control circuit in most industrial panels operate at 24 volts DC. This is done because I'll give you two basic reasons. One, for safety. And two, because in DC, we have less ripples. Your signals are clean. And so we cannot just convert AC to DC directly. We need this guy, the power supply unit. This particular one here is for Schneider. You can convert your 230 volts to 24 volts DC. You have some that are variable, 12 volt DC, like that. You convert it to whatever your component needs. And it will be able to interact with your control wiring. And like I said, that the incoming supply from the grid is typically to 30 volt DC single phase or 400 volt three phase. And that's why the PSU will convert the main voltage into a stable 24 volt DC. So again, for all the Arduino family and those that like Arduino and microcontrollers, you have to build a rectification process where you use your capacitor, you use your diode to make it DC first, then use your capacitor to filter before you send it to your relay then you can send it to your potentiometer to vary. So instead of building that complex system, your PSU for industrial system, you don't want to build something so little like that. Your PSU have a system that is assembled to handle all of that. And now for MCBs, we know what breakers do. They protect against short circuit, protect against overload. So this is one of the main components in your control panel. It is a protective device. And I'll tell you that every electrical circuit in the control panel must be protected against overcurrent. Every must be protected against overcurrent, either directly or indirectly. You must see a protection, protecting that device against overcurrent or overload. So the MCB detects, like I said, excess current and trips automatically. There are ways you rate your MCBs to know the proper one to use and all of that. And so we have different circuits that have different MCB ratings. A 16 amps MCB for something like a motor circuit, a 6 amps, let's say for mostly control circuits. You would see, let's say, a 2 amp MCB for 24 volts instrument supply. So selecting the right MCB is part of the design process. And if you select this, EPlan will allow you to document this precisely. So next, I'll be talking about is the contactor. So a contactor is essentially a heavy-duty electrical operated switch. So if what is basically inside the contactor is, the principle of electromagnetic induction, where it says if you wound a wire around an iron and you energize the wire, it creates a magnetic field. And so if you energize the coils of this contactor, a magnetic field is created inside. And you see that the metals inside attract, and the plungers attached to those metals change direction. So I'm not sure you can see my mouse, if you can see my mouse cursor, this point is directly connected to this point. So this will not be continuous. That is, there's no continuity between this. But immediately you energize this, and those two metals inside this contactor attract, the plunger change position, and this becomes closed. So that is why they say it is used for switching. It is used for high power loads. And for contactor, it is used for high power load. So you have the internal components of the contactor are way much more. So from the coils to the metal plates to the plungers, they can handle high current. And a relay is a smaller version of a contactor. You energize you hear the attracting sound, those terminals change positions, but a relay is meant to handle very little current. So these are the components you'll be seeing in a control panel. And for the terminal blocks, in a control panel, if you see a controller, you notice that every wire goes from inside the panel to a feed device. If you are looking at the control panel, let's say you have a control panel and you have a motor outside the control panel. You don't want to put your electric motor inside the control panel and allow the control panel to be shaky. So every device, let's say you have your contactor, you want that contactor to control a motor outside the control panel. Signals from the contactors are connected to the terminals. And the other end of the terminals are then connected to whatever devices you have outside. So you don't want to have a system where you just drag all those cables out because they are signal cables. And for the other part of the cable, you're now tying your motor to the cable and using black sellotape or black insulation tape to how will I put it down, to connect signal from that contactor to that particular motor. That's where your terminal comes in. You connect to one end of your terminal, the other end to whatever device. Some terminals even have fuse blocks. And it is in EPlan, you have to document these terminals. All terminals have numbers, and they can be cross-referenced to device or field cable that it needs to connect to. So this slide has basically given you, there are a lot of things on the control panel that are not mentioned in this slide, like the push button, the selector switches. You can write them down and check them online. It will help you correct. You have meters, you have a whole lot. But basically, these are the things you will see in the control panel, in the PLC control panel. Okay, so at this point, we will be taking attendance. Yes. So we'll be going on a break to take
Yes.
attendance.
Yeah, so the link has been dropped in the group already, on the chat already. So it's a Google form. So please just click the Google form. It's going to be live for the next 15 minutes. So please just quickly, I don't know if there's a way to pin the message. Anyway, if you check, you see the form. Just click the form and make sure you fill it so that we can take your attendance. And if you have any questions, maybe you can type that in the chat as well, just so that maybe if the instructor wants to pick that. But just make sure you fill the form. It's going to be live for the next 15 minutes, but we are just giving a 5 minutes break for you to fill the form. So, Alfred, feel free to resume anytime from 11:45 or 11. Let's say 11:47, 11:48, around that time. Feel free. You have 5 minutes from now.
Okay, no problem. Okay,
Thank
no
you.
problem. Thank you
Thank
very much. Yeah. So the attendance code has been dropped. Yes, the attendance code has been dropped too. Okeshola Tosin. Can you unmute yourself?
Yes, can you hear me? Hello,
Are you there?
can you hear me?
Yeah, I can hear you.
Sorry, I'm trying to break up the chat, but it is not coming up.
Oh, okay.
Yes, I don't know why.
But have you seen what you want?
So I can't see it because the chat is not coming up. I can't see the attendance here.
Oh, maybe you quickly
Maybe
log out
exit
and
the
log in.
meeting and come back here.
Yes.
Okay, let me do that.
Okay. We'll share it now. I think that's it. Oh. Okay, Larry King. I'll just take one question. You can unmute yourself.
Hello, everyone. Thank you so much, Mr. Fatuna. Thank you, Mr. Alfred. I just wanted to find out what time the break will be. What time would the break over?
Okay, so it's almost over. Let's just say next 1 minute. Temidayo, can I ask a question?
Okay, thank you. Thank you very much, Alfred. So I want to ask a question. Can I ask it now?
You can.
Okay,
What?
okay.
Okay, that's it.
Okay, so basically it's about the terminal blocks that you mentioned that
Yeah.
fuses, right? I basically just got to know about that like 2 weeks ago. 2 weeks ago. So I wanted to ask, why do they have fuses? Right? I know what a fuse is, but why the terminal blocks? Why do they have fuses? And how different are they from the regular terminal blocks that don't have fuses?
Oh, okay. So the ones on the one on my slide. Let me go back to my slide. So, 1 minute. You can see the one on my slide, right? So the one on my slide, check from the first point to the second point. They are just basically metals connecting this first point to the second point. There is no protection. There is nothing. It's just like saying immediately you connect something here. It is very mechanical. Current flows through this place, goes to where you are sending it. But now, for fuses that have terminal blocks, you can see there are different reasons. So one reason is instead of you relying on, shall I say, the upstream breaker now to protect the whole circuit, or if a fault occurs, a fused terminal block we allow that for each outgoing wire or devices, it has its own protection. And so if a fault occurs, only that specific line is not affected, it's also protecting the whole panel from being affected. So it also, I would say it prevents cable damage up to I said it before, equipment protection. I would say easy fault isolation and maintenance. So if you have, there are some fuse panels with fuse terminals with indicators. There is a problem, it indicates the fuse is out. So you definitely can easily identify that, oh, there's a blown fuse here. This point is isolated. Do you get it? Okay, sorry, I think you are still muted. If you get it, just give me like a reaction or something. I can't remember your name. So we will continue with what will I call it now? We'll continue with our slide, continue with the class. It's supposed to end by 1. So we have basically 1 hour, 10 minutes to end the session. I hope everybody is enjoying this session. So if you are still with me, I want to get reactions, please. Thank you. So I know that we are still together. Yes, thank you. And so let's continue from where we stopped. So our next slide, we're talking about the 3 words of industrial automation and basically where EPlan sits in it. Let me move this down. So I would say every time an automated industrial system is designed, either it is built or commissioned, three distinctive engineering worlds come together. 3 basic distinctive engineering worlds come together. So these 3 worlds will involve different people, different tools, different skills, but they are deeply dependent on each other. Deeply dependent. And the quality of your work as an electrical design engineer directly impacts the success of the 2 other worlds. So if we are to walk through each one of them, we'll say the first word is the EPlan, is the electrical design, and that's where EPlan lives. So if you're seeing this logo, like I said before, EPlan is wide. EPlan P8 electrical schematics, Pro Panel, 3D, there are smart productions, Cable Pro D. This one is cable routing. If you want to see cable routing in 3D, there is Harness Pro, there's engineering configuration, there's pre-planning. So EPlan is like another world on its own, a very beautiful, big world on its own. So, but we are here focusing on electric P8, which I said is like the mother of the whole stuff. And so the electrical design, like I said, engineer is responsible for everything that happens on paper, or more accurately on screen, before the panel is physically built. So this includes you designing the panel layout, deciding what components go where in the enclosure. That's after your conversation with whoever wants to, the client that owns the panel, how they are mounted, how those devices are mounted on D-rails, how cable ducts are arranged, and how space is needed. So another point where EPlan comes in is producing electrical schematics, like we have been saying. The multi-page drawing set that shows every component, every connection, every wire, every terminal, every protection device, and every control signal in the system. This is like I'll say is the primary deliverable of electrical design engineer. And it is what we will spend, I would say, majority of this training producing. You will be producing electrical schematics. Another point is creating wiring documentation. Like I said, terminal diagrams telling you where to connect, what to connect to each diagram, cable schedules, and connection lists that tells the panel builder exactly how to wire every connection point inside the panel. and between the panel and the field. So how you're wiring inside and how you're wiring outside. EPlan will also help you to generate reports including bill of materials, device list, cable list, terminal diagrams that are automatically produced by EPlan from the data embedded in the schematics. So this report goes to the, let's say, like the procurement team. So that's why I said EPlan is their mother. EPlan this one now, you are producing all these components and it can go to the procurement team for ordering parts. This document too will go to the workshop for fabrication. And at the end, will still be needed for installation and commissioning. Will be needed for reference. So the professional title for this role varies. So you might see, they might call it electrical design engineer, control system design engineer, panel design engineer, electrical card engineer, but their work are basically the same. You are producing a complete, accurate, professional set of electrical design documents. And I'll tell you, the tool used for this work at the professional level is EPlan Electric P8. And so if we are talking about the world 2, which is the PLC programming, like I said, I'm only referring to PLC program because I'm just making you look at a control panel with a PLC. So if I'm taking PLC programming away, I would say somebody that designs the relay logic of the system. So let's assume there's no PLC. And we are now replacing PLC programming with somebody that will say, okay, I have two contactor. What is the control sequence or the control system I want to build? What connects this to this? Okay, when you have normally open, close this. When you have normally close this. Manually draw it on paper first, then they transfer it and all of that. But if you're talking about the PLC programming system, that's where you have another engineer. So once again, I'm not saying you can't do the two, but in a professional setting, you don't want to be designing panel and now be programming the PLC again. That's where division of labor comes in. And while the electrical panel designer is designing an EPlan, another engineer, the PLC programmer or automation engineer is writing the control logic that will run inside the PLC. The beautiful thing with EPlan is it's the communication is it comes in two ways. So I can design something on EPlan and send to the PLC programmer, and it automatically appears on your TI portal. You see all the PLCs, all the PLC, all the DID, all the card I use appearing on your TI portal. At the same time, somebody can decide to do the whole connection on TI portal, then export as XML file, import in EPlan, and boom, you have all your PLCs, input card, output card. You are not manually doing anything. So the communication is there. The advanced type of EPlan is there is EPlan Cloud, where you don't even have to be there physically. Another engineer can be somewhere else, still working on the electrical drawing you are working on. So EPlan is very beautiful. And talking about the PLC programming, I would say the control logic is the software that makes the system behave. The brain of the system, it tells it what to do. It defines the sequence of operation when the start button is pressed. Check that the emergency stop button is healthy, that is, it's normal. Check that the motor protection is not tripped. Then energize the contactor. Then it transfers to the terminal that starts your motor. You can put a timer after 10 minutes, after 10 seconds. Make sure, let it run a star. Then after that, let it move to delta. If there is a fault, raise alarm. All the languages you are speaking, everything is inside the PLC program. So, and you can use environment like the TI portal, RH Logic 5000, Code Cs, the Schneider programming environment. There are some that even the HMI and the PLC are embedded together. You have WinTech, you have a whole lot, depending on the PLC, everything, all kind of logic you are doing depends on the PLC platform being used. And here's why your work is, as an electrical designer, is critical to the PLC programmer. The PLC programmer needs your IO list. The IO list is a document generated from EPlan project. It basically tells the programmer exactly which PLC input or output address corresponds to which physical device. So, for example, you can have, let's say, for those of you that are conversant with TI Portal, I can say, okay, PLC input I0.1 equal to, you have something like start button X1 terminated at X1:1. So you are making sure that everything you are doing is accurate. And if your EPlan documentation is inaccurate, is incorrect, PLC programmer will write logic based on wrong addresses assignment. And then you have to go back, start manually checking for what is connected to which IO. When the panel is built and the PLC is programmed, if you don't do this, nothing works correctly. Commissioning team will spend the whole day tracing unnecessary fault that should never have existed in the first place. So this happens in the real world more than you think, especially in Nigeria. It happens a lot. And I would say it's always comes back to poor or inconsistent electrical documentation. So your EPlan drawing are the foundation on which programmer builds the software. So you want to make sure you get the foundation right and make sure the software works. If you get it wrong, the whole project suffers. And now I'm talking about the third world, which is the installation and the commissioning environment. This is like the physical world. And if we're talking about the physical world, we're talking about the workshop, we're talking about the site, where the panels are built, where they are commissioned, connected, taken to your prospective clients, connected to factories and all of that. And the panel builder takes your EPlan documentation, the schematics, the terminal diagrams, the wiring schedules, and use them to physically assemble the panel. They mount those components on drilling rails, that's for the construction, they run cables to cable ducts, terminate every wire at correct terminals, label everything according to your drawing. And I would say a professional panel builder can build a panel like I said, mentioned earlier, they've never seen, purely from good documentation. And this is the standard you want to build in. Even if you are building a simple direct online 1-page or 2-page power and control page, make sure you follow these things. And so if these panels are built and delivered to site, the commissioning engineer, sometimes the same person as the PLC programmer, will have to power the system. The person will verify that every input and output works correctly. They will load the PLC programmer, they will load the PLC program, and they will run the machine through its operational sequence for the first time. So they are using your EPlan drawing constantly through this process to trace signals, identify terminals, verify wirings, and troubleshoot any issue that might come up. So if documentation is not there, then you want to make every engineer on site crazy. And so at the end of the project, your EPlan documentation is updated if any changes are made during installation and commissioning. So while the commission, they change the position of this to this, note it down. You are going back to input it in your documentation, making it the as-built documentation, making it the origin. So we don't want to have part 1 and part 2. Any changes, go back, make that change immediately, because you don't know who would need documentation. And this is like the permanent record of exactly how the system was built. So most times you see this documentation in the client's engineering archive. Some will even put it inside the control panel, and every time there's a problem, they pull out this documentation and say, hey, what is connected here? What is connected here? So I want you to genuinely appreciate that your EPlan drawing directly supports all three words. They are not just a design exercise. They live engineering documents. They are like, I would say, let me put it in this way, they are life engineering documents that real people depend on to do their job correctly. So if I go to a site, I once had issue with an engineer on site that was shouting that it was not correct, and I was like, where's your documentation? And he told me, this is not the first time I'm installing panel, and I just walked out and I went home because I'm not saying I just went there to assist, and he was so bold on the fact that it's not installing panel for the first time. And it does not need this is where it is to connect it. It was just wasting my time, and I just had to leave. And we had to go back when there was proper documentation. It was not as if the panel was so big. It was not so big. We could do troubleshooting and correct whatever faults was there. But then we'll put ourselves at risk, put our company at risk for an engineer that does not even have documentation and wants us to just touch whatever we want to touch. So you should make sure that you have the proper documentation. And like I said, documentation or not, you might still see systems where there is no documentation or where you have documentation that is incomplete. And so having the background knowledge of good symbols, having background knowledge of your IC standards and all of that, what is connected to what, you should be able to pull through during troubleshooting. So once again, let me get like your reaction. Let me be sure that people are not sleeping after the break. Okay, thank you. Now we'll be moving on to the next slide. So the slide is a lot, but when it's one, we'll stop. Don't worry. So here we'll be talking about the industry standard electrical card. So if we talk about EPlan itself, because I'm sure you've heard so many things about EPlan, but I want you to understand that not just what EPlan, I don't want you to just have the idea that, okay, this is EPlan, this is EPlan, but I want you to know that it is the tool of choice for professional electric design engineers around the world. So like I said before, EPlan is a professional engineering device platform it was developed by EPlan Software and Service. And it's a German company with about over 30 years of experience in engineering software. And I bet you it's used across virtually every major industrial sector, automotive to manufacturing, oil and gas, food and bev, pharmaceutical, wastewater treatment, power generation, marine, a whole lot. So when we say EPlan is widely used, I want you to understand that I want you to understand that there is more to why EPlan has been used, EPlan has been chosen. So you see that even big companies like BMW, Siemens, Bosch, Volkswagen, ABB, and thousands of them use EPlan as their standard electrical engineering tool. So if you're applying for a role as an electrical design engineer at a serious automation company, I bet you anywhere in the world, EPlan is one of the proficiency. EPlan proficiency is like one of the most valued skill on your CV. One of the most valued skills on your CV. So I'll tell you that EPlan is not just a drawing tool as related to like AutoCAD. AutoCAD has some good stuff, but can never be compared to EPlan. AutoCAD has a whole lot of mechanical things you have to do in it. But EPlan is not just any drawing tool. It is It is database driven. It is a beautiful platform that you want to work with less stress. Though it might be complex to learn as related to AutoCAD, but an AutoCAD too has its use. But I bet you, as an industrial electric control panel designer, you want to make sure that you build your knowledge on EPlan. And so if we now go to talking about the differences between EPlan, Autodesk, and manual drawing, don't think manual drawing is phased out. I bet you even before you touch that EPlan software, you want to quickly just do that manual drawing on your Jotter and say, will this thing work? Will this? So I would say when most people hear electrical CAD, they think of AutoCAD. Or should I say more specifically, as regards to what we are talking about, AutoCAD electrical. So it is used by some engineers for electrical design, but there's a fundamental difference between how AutoCAD and EPlan electric PH work. And that difference has enormous, like a whole lot of practical consequences. So for AutoCAD at its core, you are drawing lines, you are drawing shapes. Highest you get DWG files from these OEMs. And when you place a symbol for a circuit breaker in AutoCAD, I would say, draws a graphical representation of circuit breaker on your screen. It looks like a circuit breaker, but AutoCAD does not inherently understand that it is a circuit breaker. It does not know that it does not know the circuit breaker rating, the manufacturer, its part number, and a whole lot. If you import a file on EPlan, let's say a file you downloaded on Siemens portal, then you will know that there are a whole lot attached to that thing. Part numbers, this one, the contacts, pictures, this all just in one. So AutoCAD, it does not know which other symbols in the drawing are associated with the same physical device. I would say it's sometimes cannot even automatically cross-reference between pages. And that's one beautiful thing about EPlan. If you tag your devices well, if you like, use a contactor on page 1 and go and use the open contact on page 1000, sheet 1000, you will cross-reference to that part. Still cross-reference to your table of contents where you have those things. So EPlan is beautiful. EPlan is smooth, makes your work, and not just the software, up to your PDF. The cross-referencing option is there on your PDF. You export your drawing as PDF, you do that, EPlan brings it out. EPlan cross-reference tells you have used this device here. This device is connected to this. Oh, this power supply was coming from here. To even tell you it's coming from power supply something, column something. So you are not just going to a page and you're just looking for everywhere. Where's this thing? Where's this thing? It is there. It is. So if you understand EPlan electric, you know that when you place a component in EPlan knows it is a specific type of device, a circuit breaker, a contactor coil, a terminal block, a PLC IO module. Every component you place in EPlan exists as a device record in a database, especially when you're importing the EDZ file. Even if you manually want to draw that device, you go to the Properties tab and you assign it under the Part Management, and you say, okay, I'm putting it under circuit breakers and this. All the parts for this thing, you can always fill it. You can put a part number, you can put current rating, you can put this, you can put that. You can have a device. You can generate just one device and its specification and you can modify its specifications. So I'm not talking about the EDZ file now. Let's say I draw a contactor, but I want to make sure for anybody that uses that contactor, there are different specifications to that contactor. So I don't want to start importing 1 million contactors. I can have one contactor, put it in, a tab comes up, input the voltage, input this, input the part number, input this, for just that one component that I drew. So this is like the level at which EPlan has gone. And because of the database foundation, EPlan can do things that no manual drawing tool can do. For now, no manual drawing tool. They might bring us something later, but EPlan is still the best for now. And if we talk about the automatic cross-referencing, I said it before that when you place a contactor coil on page 20 of your schematic and its auxiliary contacts on page 5, EPlan automatically adds cross-referencing annotation to both symbols, telling the person that will read that control panel that this coil contact is used on page 5, column this, and this contact belongs to the coil on page 20, column this. You don't need to like type these references manually or say, okay, while we are using this coil on page this, you now have one jotter and say, let me remember that I use this coil, this normally open on this, on another page. EPlan generates them automatically and updates them instantly if you move anything. If you move that device to column 4, it goes across all page. Another beautiful thing is the automatic reports generation. So if your schematic is complete, there are places on your EPlan where you can generate bill of material, like I said, device list, cable schedule, everything you need. And these reports are not separate from what you did. They are getting it from the drawing you've done. They are live output from your project database. You change a component, they change automatically. So EPlan also have built-in error checking. Same way you have on your PLC where you write code and you compile and you say, it's telling me that line 1 and line 2 is not correct. There is a place on EPlan where you can do your error checks, where it can tell you, duplicate device tags. You have two contactor and you name the two KM1, KM1. To tell you unconnected terminals, to tell you missed cross-referencing, devices with no part number assigned, how will I put it now? It will flag everything for you to correct. And I'll say this kind of automatic quality checking simply does not exist in a traditional drawing tool. And for the last point on my slide, which is the full BOM and parts management. BOM is bill of materials. So EPlan will connect to part database, including the EPlan data portal. So I don't know if you've heard. Okay, EPlan data portal is like, let me say it's like an online database where you can see you see a whole lot of devices there from different OEMs, from different manufacturers, Siemens, Schneider, Phoenix, ABB. The beautiful thing is Siemens, I think I read it somewhere. Siemens wants to, in a way, start adding advanced function on the plan. They want to companies are making sure that every of their devices is EPlan standard. They are producing EDZ files for everything. You say, I have EDZ file for this, so I don't need to like manually draw anything. If I download Siemens EDZ file and I put it into my parts management list in EPlan, I have everything I need. If I upload it, you're already seeing it. PLC 1200, 5 volts, 16 IO. It comes with it. Very beautiful thing to build. And so when you select a specific device from that EPlan portal, all the technical data is embedded in that design automatically. All the technical data. So I'll tell you that the conclusion about these three things is clear. For professional industrial electrical design, especially for PLC control panels, EPlan electric PLC is an industrial benchmark. Very important. Manual drawing is essentially no longer acceptable. Where manual drawing comes in is during the first thinking thoughts or first thinking procedure, where you're having your first thoughts. You want to know, you don't want to just draw normally open and normally close, then start pressing Ctrl A and delete everything. You want to do like a simple sketch on your paper. That's where manual drawing comes in these days. But apart from that, it is going after that, you are putting it in your EPlan. You will not draw manual drawing and just tender it as you can do a manual drawing and use it in house or something if you say, but you will still not like, let's say you are doing a simple explanation or something, and tell everybody to just go through the process and all of that. But if you are making it very professional, then you are using a professional tool. And I would say AutoCAD electrical, it has a space. It also has its place in the industry, but for the level of documentation quality, automation, and integration that the modern world industry demands, I would say EPlan is the professional standard. And so we'll talk about where EPlan fits in a real life project. So understanding the workflow will help you see that EPlan is not just involved at one stage. We have said something similar to this before. It's customer specification, electrical design in EPlan, panel fabrication. That's when you are working in the workshop, PLC programming, site installation and documentation. What else? A whole lot. But I want you to always know that uh, I want you to notice something important in the workflow. EPlan is not involved at, shall I say, EPlan is not really involved at, shall I say, step 2, but it influences every step that follows. So the quality of step 2 determines the ease and success of step 3 to step 6. A poorly done EPlan project creates problems at every subsequent stage. A well-done EPlan project makes every subsequent stage smoother and more professional. And I'll tell you that because EPlan is a live database and not just a static drawing, changes you make, I've repeated it several times, that changes you make at any stages reflect immediately across all reports and cross-referencing. And your documentation is something that you want to take very important. So if you are getting to know, this stage will help us know what the EPlan workspace looks like. So if you open your EPlan, okay, sorry. Let me see if I can open my EPlan. This is a screenshot, but I'm trying to see if I can open my so let's just continue. If it loads quickly, then I'll take you through some of the things you'll see. But then checking from this place, you will see the menu bar. You will see that contains file, home, insert, edit, view. This is the menu bar. And below it, you see the ribbons. You will see this, you have your pages, you have your insert center. This one is one very important part where all your devices comes in. You see devices here, you see electrical, okay, it's still loading. You see electrical, let me bring this down. You see electrical symbols. If you import a device, you see it here. Window macros. So I'll just give you a basic idea of what macros are. Those that are, okay, or should I say, if you draw an electric circuit now let me use this. Let me use what is showing on the screen. This is a circuit for a normal direct online connection connected to a motor start and stop sequence. So, but I know I have 13 motors in my field with this exact same connection. And you definitely will want to be doing drag isolator, drag contactor, drag the contact, label it, and all of that. I can create this whole page as a macro. I'll create it as a macro and it will be reusable in other pages. So I'm just doing copy and paste in other pages, copy and paste in other pages, then assigning the tags. So it is saving me from so many problems. It is saving me from a whole lot of manual redrawing and pasting those devices there again. So there are a whole lot of things, tags, if the recent stuff you've used, different things on the master data is like one of the most important parts. Let me see if my EPlan is on. Okay, so for the master data, that's where you'll be able to import parts from different OEMs. You'll be able to create your plot frame. We'll explain all that later. You'll be able to create your forms. You'll be able to create symbols, do a whole lot of things. Apart from that, sorry, I'm changing slides, but I'm just trying to prepare this so you can see better. Devices, you're seeing it. If you choose this navigator, that means you want this particular part labeled PLC. You want to have a tab that tells you everything about the particular PLC you are using. So your navigators bring down a side tab that give you more information about whatever you are doing. So if I'm choosing a navigator for terminals, it gives me a tab there that tells me more information about the terminals I'm using. Let me see if it's still 1 minute. Okay, so while it's still loading, I'll still want to show you. So like I said for the macros, if you have for the macros, you can reuse them. You can do a lot of things for your master data. You can import, you can create symbols, you can create plot frame, you can create your title pages. Insert, where you have another very important part, you insert your connection types, interaction points, different things. So if you know how to use all this well, the environment is rich enough for you to understand whatever you want to do. It is very rich. I would send, maybe later on, I'll send an EPlan manual that will even guide you through, where you even tend to learn even more advanced things when you are through with the basic ones. Let me check again if, okay, it's still loading. So this environment is, it basically, it basically tells you everything you need in a plan. It basically shows you everything. On this insert center, I can just use, if I don't know the name of the device I imported, but I have the part number, I can just put the part number here and it pops up. So I don't even necessarily need to write a circuit breaker or a this. I can just have the part number of all the devices I imported into EPlan, and you see everything. So you are manually not trying to import something or doing things in a very hard way. Okay, so this is one environment. This is the 3D. Okay, so if you can see my EPlan screen, if you can see my EPlan screen, please just indicate. I'm coming. So if you can see my plan, if you can still see my screen, just indicate before I switch to my plan screen. And okay, now I'm still on the presentation screen. I want to confirm that you can see. So if you can see my plan screen, kindly indicate too. Okay. Okay, so this is one project. We have different projects here. These are just sample project I was playing with, but this is one very standard project. See how they are. Let me try to, okay, let me talk about the menus. And so for home, they are similar to your Microsoft Word. You should be able to know how to navigate how menu bars are structured in Microsoft Word. It's as simple and easy as that. So, but you have your home, you have your insert, where you have all your connection points. I want to connect. You can drag these different options. You have your cables, your shield. That's if you have a screen cable and you want to include it in your diagram. Everything is. So you see that this is a phonics contact imported from phonics website. 24 volt DC, 20 amps, has a tag name TB. This one will be in our next section. How devices are tagged. And if you see this, it's telling you that we have 1, 2, 3, 4, 5. 5 cables. Black, BK, GY, BU. We'll get to learn everything later. So these are symbols for your terminals. Yeah, these are symbols for your terminals. This is overload and short circuit. So we'll still talk about electrical symbols. So and I'll send a document that will show you different sample of how electrical symbols look like according to IEC standards. And this one is the interruption point. So this is telling you that connection is coming from GAA, is coming from this point and it's coming into this page. Where is it used? It's used on page 2, column 9. So I don't need to put everything inside one page and infuse everything and make it so rough. This one is telling you that this same connection point, your bus bar is going into another page and it is going to page 1, column 0. That's where it starts from. Let me see if I can cross-reference to 1 minute. So see, I just left that page, came back to another page. I can still takes me to another page. Same line 1. It's telling me everywhere line 1 is used. I don't need to manually start searching for where this is line 1, where this is what you. And let me make something clear. In real life, it's not as if this bus bar will run. I want to make it clear. It's not as if this bus bar will run across different control panel. So picture it in this form. You have a control panel with so many devices attached to a bus bar. But now during design, you cannot just say because inside your control panel, you have everything attached to a bus bar. You will now squeeze everything inside a bus bar. No, it is wrong. So you are just trying to make your documentation clear enough. For the fact that I have a device here running on this bus bar, and on another page, I have another device running on this same bus bar. It means if I'm building it physically, depending on the physical arrangement, it's telling me that on all these bus bars, there are devices arranged on it. I'm trying to get a picture of, let's say, I'm trying to get a picture of a control panel so that I'll show you how a bus bar runs. So if you see this, you know that you're not just saying because this bus bar is running like this, running to another place, you have multiple control panel and you're making it run through several cabinets. No, it's just running through one cabinet. Let me show you an example. I will have to send, so just give me some time. I'm sure you can still see my screen. Just while you're waiting for the file, just relax. Sure, it's been a lot today. We'll soon end the session so we can take questions. So maybe by 12:45, we'll end the session for today so we can take questions. So I'm trying to show you what a bus bar looks like. It's a copper, mostly we use copper materials. So it runs through, especially for power, what's it called now, control panels. You will see those very big, bus bars. And you see different things attached to it. So, 1 minute. Okay, so, two, okay. So if, let's say, you can still see my screen, right? Okay. So this is what the bus bar looks like. This is what the bus bar looks like. Large bus bars with different things connected to it. This one, we don't even have so much connected to this. If you see this, you see cables connected to it. What's at the back of this cable is, at the back of this plate is MCCB control panels, MCCB breakers, sorry. Something similar to this. These they are using bus bars, these they are using cables, depending on the current carrying capacity. And you see these very hefty bus bars. Below here, this one's connected to this bus bar are ACBs, very big bus bars. So because I have the physical representation or the real life view like this, that does not mean in my EPlan, I'll now put MCB, I'll put MCCB, I'll put everything and jam pack everything on one page. No, you will section it. You will know how to section your power. Now there's a basic industry practice, like there are good industry practices that tell you how to section it. Okay, let's put our power here first. Let's put our control devices here. Let's put this here. Then when you are done, you know that, oh, all this run through these bus bars, all this run through another bus bar in cabinet one, in cabinet. This is exactly what I am saying. So look at this left part. You are seeing A1, A2. They are definitions for all this and symbol, plus symbol, equal to symbol. We will explain all that later. So equal to is like saying this is the function, plus symbol, addition symbol is like telling you this is the location, and symbol is telling you this is the document type. So there is a table that explains what AAA1 means, what AADB means, what EFA means. We'll explain all those later. And so you see that, oh, they've taken their time to say, okay, under AAA1 document, I have title page, material, safety this. This does not need to be in any location inside the control panel. That's why you're not seeing equal to sign. There's no location. It's a physical device. So you see table of contents. So all these ones are just documentations and all of that. When you get to some places like this, you will see this is still, location is not there because it's still documentation. But documentation for which part of the panel? Enclosure 1. The part list inside enclosure 1. But there's no equal to because there's no location. They are not saying go inside this panel and you will see the paper inside this place. No. But when you come to places like this, you see, let me look for places like this. It's telling you that this location is for, this function is for 400 volts. Let me open the page. 400 volts. This is it. It's telling you the function of this page is talking about 400 volts power supply. This is your power supply coming from this place. This is the bus bar. It's telling you where the power and all of that comes from. Then plus is telling you it is located where? In enclosure 1. So you can have like, let me go back to my image. This is 3 cubicles of enclosure. 1, 2, 3. You can decide to say they are separated You can decide to group all this as enclosure 1. You can decide to say this is 1, 2, 3. So it depends on the arrangement you are doing. If I say, okay, that 400 volts is on enclosure 1, I can say the 400 volt, this is where you will find it. This is where you can put it off from. So proper documentation, if you don't do proper documentation, you will. These ones are still inside enclosure 1. It's just telling you that it's inside enclosure 1, it's still under 400 power supply, but these are the pilot lamps. I know pilot lamps are usually on the doors. I have some pictures, maybe I'll share it later. And because of this, you don't see this previous page. You don't expect me to now still put pilot. You don't expect me to still now put pilot lamp on this page, and proper documentation, best industrial practices, neat arrangements, and all of that. If you see these two, you have 24-volt power supply. So this is like what the environment looks like. Like I was saying, if you come to master data, this is its management. If you come to this management, you are seeing how your devices are arranged. Plot frame is, let me show you. Okay, so if I'm importing something into the part management system, is it a cable? Is it a sensor? It's already, if you import any EDZ file now, it will show you this is one terminal. I can decide to come this and that terminal from another manufacturer. And if I select this terminal, to show me the symbol, to show me the specification, to show me everything I need about this terminal. Like if I generate a BOM list and send it to the procurement, they will buy whatever they want to buy. So it is, let me show you, see converters. You don't need to think of how do I draw this converter. There are electrical symbols that will follow all this. There are different, too structured, should I say too structured for my liking, but then too beautiful for my liking too. So if you have something like a title page, this is what a title page looks like. This is this is where you're putting all the information. We'll still discuss all this later, but I'm just giving a somehow clear overview of what the environment looks like. See the column, you have your column. Some people even used to put on the left side, easy identification and all of that. All this below, you have the in EPlan, we call this edge like this, we call it the plot frame. The edge like this and all of that, call it the plot frame. This one in the middle, we call it the form. That's more information about what the project is. So this on the plot frame, you can have a title page and all of that. Let me take you to material regulations, safety instructions, plenty documents. So tell me how I will send this full documents to you, and you still tell me that I beg, should make I come out one thing or that. I'll not even answer. I'll say check the documents and you need everything. You need everything you want. This one will tell you what what will I call it? Wiring colors are used. Remember I told you wire colors differs with countries. And so that is why documentation is important. The person reading the document must be able to come back here and say, oh, this is it. The enclosure I use, this is it. There is no particular way to how these things are arranged on your form. But the information that are needed, symbols, it even wrote symbols in accordance to IC 76057. So it's using this IC symbol it followed this IC symbol for all the symbols it has used in a drawing. So there is nobody that will come and this is your device tag list, how it is tagged, or your tag name. From this place now, if I click on this and I cross-reference to somewhere else, it takes me to where this guy is used. It's bringing me to the 3D panel where it's used. If I say cross-reference from here to another place, it will take me to where it is used in the diagram. So I'm trying to, 1 minute. So this will show you. This is like the 3D view. If you install if you have installed this is the top view, this is the front view. You can have the front view here. So if you want to view your panel from the front, from the side, isometrically, you can view this one will come in. We'll do this if there is time. If there's no time, maybe I'll teach people personally. But this is how you design your panel, then you have something like this. This is how it will look like in real life. There is almost no difference. You have your mounting plate. It is a lot, but it is the standard, and it is what you must start building your background knowledge with. Because I bet you nobody will really put you in a company and say we want to start teaching you the basics of EPlan. You should know your basics, then they will teach you the advanced parts show you the advanced part of how they use these things. So your proper knowledge of all this is very, very, very important. But we will definitely enjoy this bootcamp. We'll do our best to make sure that even if it's just this direct online you are seeing, and we follow every standard to make sure that it looks cool, or a star delta, and then we do a small PLC 3D drawing of what it looks like. Everybody should be able to do it. And I promise you that, like I promised, I'll upload the software on the drive and also upload all necessary information you need to keep it running. Then maybe you people can walk through that. And from the next class, we'll be doing more on EPlan. We'll continue our journey on EPlan. So this is just what I talked about: page navigators, device navigators. If you come here, this is it. Home, you have your page. This is the navigator. If you press the navigator, it comes down. 3D navigator, it comes down. It tells you can add anything to your 3D. You can edit your 3D. You can decide to check only for enclosure 1, and you can decide to check the front like that. Check only the last 3D you saw the complete thing. You can say, okay, I don't want to see the complete thing. I want to see only the base plate. So you are seeing different things, and it's making your work so easy. Connections. There is also a point here where you can bring in extra menu bar. You can show menu bar here, and you will see extra things from project data. This one is report. You generate reports, parts, you see different things, macros. It's just similar to what you have above. So, but there are you watch some EPlan videos, you will not see this. Instead, you will see this. So, in case you are using EPlan P8 and you're saying, I'm not seeing this title bar on the video I'm watching on YouTube, come here, do this. You will see the full thing you want. You see different things you want, and you are good to go. So, from our next class, we'll continue with what we've been doing. We'll continue from project hierarchy. So, power, control, like that, how it is supposed to be arranged. No, to my knowledge, no industry standard really attached to this, but they are industry best practice. You should know how to arrange your room very well. So power, yes, all the powers here, sheet 1 to this, all the controls are here. We have emergency safety here. You don't want to just walk in here and be looking for things up and down. So from our next class, we'll talk about that, talk about drawing standards, IC, and we'll do a simple project. So we might want to rush from the next class, but hopefully from the next class, we should have our PLC, we should have our EPlan installed by God's grace, and we'll all be fine. So, okay,
All
I
right.
see some.
Yeah, Alfred.
So,
Yeah,
yes.
thank you so much for such a wonderful session. I think we just if people, I think I should drop my hand now. So we just want to take one or two questions. Because the class is going to end by 1, and we are trying to keep to time. So Kwagana Saifullah, please can you just unmute your mic, and for the others, maybe you can type your question. Yeah, let's just keep the questions brief, less than 30 seconds. All right. So Kwagana, you can ask your question if you still want to. Okay, seems it's not ready. Emmanuel Adeboye, can you unmute your mic and ask your question? Okay, I assume the person is not ready. Olonode Julius.
Oh, okay. They need somebody to unmute them.
Okay,
Yes,
I've unmuted Olonode,
I'm on.
yes.
Yeah, good afternoon, sir. Good afternoon, Mr. Alfred. Good afternoon, Mr. Adimeji. Yeah, thank you so much for this course. Yeah, I actually have one question, and my question is that having designed on EPlan, can we use our file from EPlan on AutoCAD, or can we use AutoCAD designs on EPlan? Is there a connection between the two of them? And also, I want to ask, AutoCAD electrical, we used to have breakers there designed already and cables too. So I don't know, is there a leverage between AutoCAD electrical and EPlan? So that's my question. Thank you.
Okay, so let me quickly answer that. I spoke about that before. For the first question, you can bring in DWG files from your, what will I call it now? From your AutoCAD into ePlan. So because I know ePlan AutoCAD uses DWG files, but if you import DWG files into ePlan, you don't have this automatic wire connections. They are almost just like a mere symbol that you drew. So even if I'm importing DWG files into AutoCAD, I am how will I put it now? I'll have to create it, edit it again to be a symbol, be a usable symbol in ePlan. Put in connection points so that if I'm moving in across a circuit breaker or something, I'll be able to what will I call it? I'll be able to automatically connect, have how to tag all those things. So the first question is even somehow related to the second, because you might have circuit breakers and all of that on ePlan electric, but what I said is the details you have as regards to those components can never be as comprehensive and complex as what you have on ePlan. So you might have a circuit breaker on ePlan electric, but is it telling you the part number? Is it giving you the connection point? Is it telling you so many informations you need about that particular device?
All
So
right.
I would say, yeah.
Sorry, I didn't know you.
No problem, no problem.
Okay,
I'm
so
good.
Kwagana, let me ask him to unmute if he still wants to ask. Are you? Oh, I think he muted himself back. So, Abdul Kabir, I've asked him to unmute.
Okay. Abu Kabi, you can unmute yourself.
Good afternoon, sir.
Good afternoon.
Okay. Thank you very much, sir, for all your explanations. So my question is that it seems so far that ePlan is used mostly for documentation. Now, so my question is that can we in any way simulate like these designs that we've been like doing on ePlan? Is there a way we can simulate it to know if there's any fault in connection or something like that?
Okay, so first, I want you to clear your I don't know the idea you have about what you mean by documentation. So it's not like you are just I'll take it from two angles. It's not like you're just listing things or you're drawing circuits. Drawing the appropriate circuit is still part of documentation. So I'll take your knowledge of documentation as everything from your schematic wiring to your cable list to your devices. Documentation is not restricted to, let's say, you just want to list something, want to draw something. Everything about that component must be documented. How you connected everything, how you did. And for the simulation, EPlan does not have a simulation. And so why it does not have is, I really don't know. But technically to me, it's if I'm designing a very complex system, I don't know if they'll put it, but it will be a lot to start simulating and start. That's why you have the error checking um, feature to at least tell you that this place is not connected, this place is not connected. And since you don't have the simulation part, you must be very careful when designing your part. I know CAD eSimu used to have documentation. It used to have simulation, but it's still not as complex. It's still very basic. So the simulation thing will even still, if you start doing simulation for a very complex electrical design, it's already becoming a bulk of work. I don't know if ePlan will put that feature on it, but for now, there is no simulation to use simulating your electrical drawing. Are we good? Okay, so I'm seeing Elijah. You can unmute yourself.
Okay. Okay. Good afternoon, everyone.
Good afternoon.
Okay, so my questions are, first of all, I really enjoyed the class. I was able to assimilate like 90% of what you presented here. So my questions now, because I'm really interested in what's going on. So I'd like to know on weekdays, like from tomorrow, because I believe the class will be continuing all through tomorrow, all through next week and upper week. What time will it be on weekdays? That's my first question. And my second question is, I noticed that on the portal it was stated there that the class is going to be hybrid. Now I'd like to know at what point will we have to come physical? Because actually I'm working, so and I
Yeah,
really
we are all.
want to, I really want to engage, and so I want to know. Those are my two questions. Thank you.
Oh, okay. Okay. So I'm sure you did not join from the beginning of the
Okay,
class.
please let me answer that.
Okay.
So
Okay.
we announced the times and maybe but you didn't join maybe at the beginning. So it's Tuesday, it's Saturday, Tuesday, and Thursday. For this first half until the time changes, Saturday is 10 a.m. Tuesdays and Thursdays at 8 p.m. And those should run typically for 2 hours, the weekdays, while the weekends run for 3 hours. Then the hybrid will communicate that if you're on the WhatsApp group, we'll communicate that to you so that you can know exactly when we'll let you know in advance. But for the initial, particularly for this e-plan, it's mostly going to be online. For the PLC part, maybe a lot of it will be online, but then there will be a point when you're trying to actually test out your project and all, where we can have physical sessions. And given the volume of people, we are trying to figure how to work that out if we're going to get a big enough facility. But we'll let everybody know. I believe you're on the WhatsApp group, right? And so any necessary information will be shared on the Bootcamp WhatsApp group. And for those that have further questions, like I said, we are out of time. Bernard, Alfred, please stop sharing. I want to share my screen.
Oh, okay.
Yeah. So okay, you stop sharing, right? So I want to share my screen. So I'm trying to see how we can finish on time. All right. So for those who are not aware, we are going to be having can anybody see my screen? Just give me a thumbs up if you can see my screen. So for those who are not, oh, people cannot see my screen. I don't know. Okay, anyway. Can you see my screen? I need a thumbs up. Just someone should just give me a sign that they can see my screen.
Yeah, we can see it.
Okay. So we're going to be we have monthly webinars apart from the bootcamp. So this is just part of our continuing development for everybody. So we have somebody by 7 p.m. this evening. She's in Canada. And we also have the bootcamp today, which is why we changed the time a little. So we are going to be the last one. We talked about PLC programming. We've talked about electrical panel design and so on robotics as well. So today we'll be having somebody to come and talk to us about SCADA systems. So Bisola Oluwabusola, I was jokingly saying it on LinkedIn, but my first interview, she was the one that wrote came up with the questions. My second interview as well, she was also the team lead that asked the questions. She's a very seasoned engineer. She has worked on projects within Nigeria, outside Nigeria. The largest SCADA project that has ever been done in this country. She's the one that headed it. So she's a fantastic engineer, very great at what she does. I don't want to go into a lot of details, but she's somebody I deeply, deeply respect, and she has contributed a lot to my career. And I believe that she's somebody that we have a lot to learn from. So I know that you already had the bootcamp today, but no prize is too great for knowledge. So I hope that you will be able to join by 7 p.m. For the others that have questions, so please, I would plead with you that drop it on the WhatsApp group. Do at me, Oladimiji Fatono, and then Alfred. I think it's Fred Keys or something like that on the group. So just you can mention us in the message, and we'll do our best to respond. So just have to respect for everybody's time. We'll be ending the session now. I would like to thank you for your time.
Thank you all for joining. God bless
Thank you.